Next, we discuss about the discharging of a capacitor. Discharging a capacitor means releasing the stored charge. This happens when a path is created for the charge to flow from one plate back to the other, effectively emptying the capacitor. The rate at which a capacitor discharges is determined by the resistance of the circuit and the capacitance of the capacitor. The capacitor will continue to discharge until it has no remaining stored charge. When the key K is released, the circuit is broken without introducing any additional resistance. This implies that the circuit becomes open and no current flows through it anymore. Where key K released means this usually means that a switch or key is opened. Circuit is broken means there is no longer a closed path for current to flow. Without introducing any additional resistance means the brake does not add a resistor or any other component. It simply stops current flow entirely, acting as an open circuit with essentially infinite resistance at the brake. The battery is now out of the circuit and the capacitor will discharge itself through R. It means with the battery removed from the circuit, the capacitor will discharge through the resistor R. If I is the current at any time during discharge, then putting E that equals to 0. When a capacitor discharges through a resistor in a simple RC circuit or resistor capacitor circuit and no external electromotive force is applied, that is, here the setting is E equals to 0. This is the equation number 1. Potential difference across the resistor V equals to IR. This is the equation number 2. It means the potential difference or voltage across a resistor is indeed calculated using the formula V equals to IR, where V is the potential difference. I is the current flowing through the resistor and R is the resistance of the resistor. This formula is a direct application of Ohm's law. Already we know the Ohm's law. Ohm's law states that the current I flowing through a conductor is directly proportional to the voltage V across it, provided the temperature remains constant. mathematical expression V that equals to IR, where V equals to voltage measured in volts, I equals to current measured in amperes, R equals to resistance measured in ohms. Potential difference V between the plates of the capacitor that equals to Q divided by C. This is the equation number 3, where V is the potential difference in volts. Q is the charge on the capacitor in coulombs. C is the capacitance in farads. This relationship comes from the definition of capacitance C equals to Q by V. It means capacitance C is the amount of electric charge Q stored on the plates of a capacitor per unit of potential difference V across the plates. In simple terms, capacitance tells you how much charge a capacitor can store for a given voltage. Since the sum of both these potential is equal to E, that is Ri plus Q by C, that equals to E. This is the equation number 4. This equation represents the loop rule from Kirchhoff laws for a simple RC circuit, means resistor and capacitor in series with a voltage source, where Ri is the voltage drop across the resistor, where R is resistance and I is current, where Q by C is the voltage across the capacitor, where Q is the charge on the capacitor and C is the capacitance, where E is the electromotive force or supplied voltage in the circuit. This equation assumes the components are connected in series and you are summing the potential differences around the loop, which must equal to the total supplied voltage E in accordance with Kirchhoff voltage law. From equations 1 and 4, simply E value substitute in the equation number 4. We get Ri plus Q by C, that equals to E means 0. Finally, Ri plus Q by C equals to 0. This is the equation number 5. This equation represents the discharge of a capacitor through a resistor. Simply, this is Kirchhoff loop rule applied to a discharging RC circuit, where I is the current measured in amperes, R is the resistance measured in ohms, Q is the charge on the capacitor measured in coulombs, C is the capacitance measured in farads. It describes the relationship between the voltage drop across the resistor the voltage across the capacitor and the current flowing through the circuit during the discharge process where the source of energy. It means a battery is removed. We know I that equals to dq by dt. This is the equation number 6. This equation expresses current I as the rate of change of charge q with respect to time t, where I means current measured in amperes, q means charge measured in coulombs, t means time measured in seconds. From equations 5 and 6, simply I value substitute in the equation number 5. We get R dq by dt plus q by c that equals to 0. We move q by c to the right hand side of the equation by subtracting it from both sides. We get R dq by dt that equals to minus q by c. We divide both sides by R to isolate dq by dt. So, R by R dq by dt that equals to minus q by cr. In the left hand side, numerator R and denominator R cancelled. We get dq by dt that equals to minus q by cr. Move all terms involving q to one side and move all terms involving t to the other side. We get dq by q that equals to minus dt by cr. This is the equation number 7. Define initial and final conditions. When t equals to 0, the charge is q equals to q naught. This means at a time t equals to 0, the initial charge on the capacitor is denoted by q naught. Q naught is a constant representing the maximum or starting charge before the capacitor begins to discharge. When t equals to t, the charge q equals to q. This means at a specific time t, a corresponding amount of charge q exists. It means that for a given moment in time, there is a particular value of charge present. From equation number 7, integrating the equation within proper limits, we get integral q naught q dq by q that equals to minus integral 0 to t dt by cr. Solve the integrals first. We take left hand side, integral q naught q dq by q. We know integral dx by x that equals to log x. So, log Q, Q naught, Q. Apply the limits. Log Q minus log Q naught. We know the formula log A minus log B that equals to log A by B. Similarly, log Q minus log Q naught that equals to log Q by Q naught. We take right hand side minus integral 0 to t dt by CR. We write minus 1 by CR integral 0 to t dt, where integral dt means t. So, minus 1 by CR t 0 to t. Apply the limits minus 1 by CR t minus 0, where t minus 0 means t. So, minus 1 by CR into t. Finally, minus t by CR. So, we get log Q by Q naught that equals to minus t by CR. Exponentiate both sides simply to eliminate the natural logarithm. So, we get Q by Q naught that equals to e power minus t by CR. Multiply both sides by Q naught, that is Q naught into Q by Q naught that equals to Q naught into e power minus t by CR, where Q naught and Q naught cancel in the left hand side. Finally, Q equals to Q naught e power minus t by CR. This is the equation number 8. We know the formula tau equals to CR. This is the equation number 9. This is known as the time constant denoted by the Greek letter tau of a RC circuit, where C represents capacitance measured in farads, R represents resistance measured in ohms, tau represents time constant measured in seconds. The time constant tau tells us how fast the capacitor charging and discharging. From equations 8 and 9, simply CR replaced by tau in the equation number 8. We get Q equals to Q naught e power minus t by tau. This is the equation number 10. The above equation represents the value of the charge on the capacitor at any time during discharging. In simple terms, this is the standard exponential decay formula for a capacitor discharging in a RC circuit. If t equals to tau, this is the equation number 11. From equations 10 and 11. Simply t value substitute in the equation number 10. We get Q equals to Q naught e power minus tau by tau, where numerator tau and denominator tau cancelled. We get Q equals to Q naught e power minus 1. E power minus 1. This is a fundamental identity from exponential mathematics. The negative exponent means reciprocal. So, e power minus 1 that equals to 1 by e. We get Q equals to Q naught into 1 by e, where e represents the Euler's number, or the natural exponential is a fundamental mathematical constant approximately equals to 2.718. So, E equals to 2.718 value, substitute the above equation. We get Q equals to Q naught into 1 by 2.718, where 1 by 2.718 means 0.368. So, Q equals to Q naught 0.368. Q equals to 0.368 Q naught. It means Q equals to 36.8% of Q naught. The time constant of a CR circuit is the time it takes for charge or voltage on the capacitor to decrease to approximately 36.8% of its initial value after the start of a discharge. In other words, after a time t equals to RC, the charge Q on the capacitor will have decreased to Q naught by E approximately 0.368 Q naught, or 36.8% of Q naught, where Q naught is the initial charge. This is our brief explanation of the charging and discharging of a capacitor through a resistor. Thank you very much. Padmam Himam.